Okay, chapter 6. Chapter 6 is a big chapter. That's what you can see from that novel of notes that you're going to do. Right now, what we've done so far, we've spent like an average of 2 or 3 days on each chapter thus far. We're probably going to spend the next 6, maybe 7 days on chapter 6. Chapter 6 is long. It's also a big chapter because it's extremely important. A lot of the things that we are introducing in this chapter are things that are going to follow us for the rest of the year. These being the notions of how we use standard deviation as a ruler, and what this thing called the normal model is. And I think actually, when we talk about the normal model, you guys have actually seen the normal model before. You just didn't know it was called a normal model. Have you seen a bell-shaped curve or heard of a bell-shaped curve before? Okay, that's a normal model. So you've seen it before, but we are going to learn lots of things about the normal model this year, how we can really model most distributions with the normal model, and how we can make inferences from that. Okay, but that's later. Today we're laying the groundwork for all of those things by delving into this idea of the standard deviation, right? All we know about the standard deviation right now is that it's the average distance of a data value to the mean, right? That's all we know. And we've kind of done a little bit with how that spreads out in a distribution, but we are going to do a lot more with it now. So the standard deviation as a ruler. The trick in comparing very different looking values is to use standard deviations as our ruler. And when I say very different looking values, I mean like if I wanted to measure, let's say we're talking about a sporting event, and I wanted to talk about who is definitively the best player. Like looking at all of the statistics, who is definitively the best player. So if we're talking about baseball, maybe offensively, we're looking at batting average, we're looking at home runs. What else? Should we look at like singles, doubles, triples, RBIs? We have like 6 different metrics, if not more, of things to look at to determine who is the best offensive baseball player in the league, right? And there are different metrics that are going to be measured very differently, right? They're going to have very different distributions. Getting a single in baseball is really common, right? As far as hits go, getting a single is the most common thing that you hit. Getting a triple is not a very common thing. Those happen a lot less frequently. So what if you have a player who gets tons of singles, but only a couple of triples? Are they better than a player that gets an average amount of triples and an average amount of singles? How do we look at that? How do we numerically talk about that? We can use the standard deviation to make those comparisons. Maybe somebody is way above average in hitting singles, but they have like no home runs and they're way below average on home runs, triples, and doubles. Maybe they're average in singles, triples, doubles, and home runs. Maybe they're way above average in triples, but low in doubles and average in singles, right? All of those things we can use the standard deviation. We can calculate the whole distribution, use the standard deviation to determine whether or not how much better they are than other people. The standard deviation tells us the whole collection of how the whole collection of values varies. So it's kind of a natural ruler for comparing an individual to a group or to compare two individuals, because it is a single number that represents the entire distribution. That single standard deviation is the same for a value here on the model and a value here on the model, right? We're using the same standard deviation to measure those things. So we can use it to compare those groups. And, as the most common measure of variation, the standard deviation plays a crucial role in how we look at data. When it comes down to it, like I said in the last chapter, median and interquartile range are used for non-symmetric, non-unimodal data. And most of our analysis is going to come from unimodal and symmetric data. And so standard deviation and the mean get used a lot more often than the median and the interquartile. In fact, as we go through the rest of the year, we really don't talk about median and interquartile range that much. It's mostly mean and standard deviation things. So it's a very common thing. It's not going to go away. All right. Z-scores. Are the notes following really well? Yeah. I went through and I checked to make sure on this one that it wasn't going to mess up. So we have this thing called a Z-score. If we want to compare an individual data value to the mean relative to the standard deviation, we have this formula. And this formula, the Y value here is our data value. The Y bar is our mean. And this is the standard deviation. And I'm going to, sorry, making corrections is hard because it's an intro. I'm going to add something to these definitions here that's going to sound a little bit weird right now. This is the sample mean, and this is the sample standard deviation. And I'm not going to, go into a big talk about what that sample thing means right now. We will eventually, but that's the sample mean and the sample standard deviation. So notice what we're doing. We're finding the difference between the mean and the standard, or the mean and the data value, right? So I'm finding the horizontal distance in the graph between the mean of the graph, which is going to be right near the middle of one of the humps, and the data value. So if I have a data value here, the first thing we're doing when we're calculating a z-score is this horizontal distance. And then what we're doing is dividing that horizontal distance by the standard deviation. Meaning, I'm taking the average distance that every data value is from the mean, and I'm dividing that horizontal distance by that. And what that's going to tell us is basically how many of these standard deviations fit in that distance, right? That's what division does, right? It says how many of this fits into this, right? If I have eight muffins, 2 friends, how many muffins do we each get? 4, because there's 2 goes into 8 4 times. That's a really silly, simple example. But if I'm talking about this numerator being the distance between the mean and the data, right? This is the distance between the mean and the data. And then we're dividing by the standard deviation. What we're finding out is how many standard deviations fit into the distance between the mean and the data. Okay. That's what this thing called a z-score does. A z-score. We're going to do a lot of z-score calculating, right? So get used to that word. So this is called a standardized value. How many standard deviations go into the distance between this point and the mean? That's a standardized value. If we do this to specific individual data points, we can find out on average how far away they are from the mean, or excuse me, we find out exactly how far away they are from the mean. But that allows us to calculate just how much better somebody is than the average. So, let's keep going here. I'm going to get off the pen. There we go. A couple things about these standardized values. First of all, they have no units. They take the units away from something. This is what allows us to calculate two totally vastly different things. We can take everybody's batting average, every hitter's batting average, and we can take every hitter's number of singles, make a distribution, find their Z-scores, and suddenly we can compare those two numbers because neither of them have units. We can just say that they're this far ahead of the rest of the average. So they have no units. Z-scores measure the distance of each data value from the mean in terms of standard deviations. So that value that we get, so if my Z-score is like 2.1, what that says is we are 2.1 standard deviations away from the mean. A Z-score of 2.1 means we're 2.1 standard deviations. Yes, it's the same. Yes, the same basic idea. It's if we're saying we're 2.1 standard deviations away, if we were looking for the exact amount of data, we could take 2.1 times the standard deviation to know that data. Yeah. So basically, what you should think of, again, remember we're talking about standard deviation as a ruler. If the standard deviation is this big, right? And a data value is 2.1 standard deviations away, then what that means is that's where my data value is. 1 standard deviation, 2 standard deviations, 2.1 standard deviations. Good question. A negative z-score tells us that the data value is below the mean, while a positive z-score tells us that the data value is above the mean. If your data value is larger than your mean, when you do that y minus y bar, you're going to end up with a positive number. If your data value is below the mean, when you do that y minus y bar, you're going to end up with a value that is below the mean. So negative z-scores tell us that it's below the mean. Positive z-scores tell us that it's above the mean. And I believe there's one more thing here. Nope, there isn't. So why do we standardize? What's the benefit of it? Well, we've converted the original units to a standard statistical unit, standard deviations from the mean. So that, again, this is what allows us to compare two vastly different things, right? I could even, like talking about the baseball example still, we could even compare things that don't have to do with baseball, right? Maybe we're trying to just say which baseball player is the best human being, right? And we can say that we can use their baseball stats to calculate part of how good of a human being they are. But we could also calculate, you know, how many DUIs they have, how many times have they been arrested, right? We can take a distribution of how many times they've been arrested, and we can calculate their standard deviation away from the mean in terms of that. Well, I mean, I would say that in terms of baseball, I would want them to be above the mean for a good human being. In terms of baseball. But in terms of being a good human being, I'd want them below the mean in terms of number of, you know, domestic services. Yeah. I mean, what we could do, so say we wanted to say, let's take a baseball player and a soccer player, right? Somebody throw a baseball player out. Let's do a current baseball player. Mike Trout, okay. Somebody throw a current soccer player out. I'm not going to say that word because I think I'm going to mess up. Ozil. Okay. So we've got Mike Trout and Ozil. Mike Trout. We have Trout and Ozil. 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 Okay. Trout and Ozil. We want to find out who's the better player at their respective sports, right? We can calculate the standard deviations for the baseball player, and we can calculate relevant soccer statistics for the soccer player, and then we can add up Z-scores to find out which one has the highest Z-score total, and maybe use that as a measurement for who's better.
But what percent is the better athlete at every sport you have to go?
So if you say if we wanted to take high school people, yeah, we could do that too. We could take if we needed to. What's the award that we get at the end of the year for? Do you guys remember what that was called? You guys know what I'm talking about, though, right? So, in general, they look for students that have 3 sports for that, right? Typically speaking, a 3-sport person is going to win that particular award. But what happens if you have 3 3-sport people who are relatively equal? Well, if you're looking for it for just purely on athletic terms, you could go into their 3 sports, calculate those statistics for them individually, do Z-scores for each respective statistic and add them up, and then say at the end, well, this person is on average better than others in each of their respective sports. Therefore, they're the best athlete. And you could totally do that. That'd be a lot of work, but you could totally do that, and that would be a fairly relevant way of counting it up, because what that does is it equals out. Say a person is there's a girl who's really amazing swimmer, state level swimmer, right? But then she's an average softball player, right? Should she be better than the person who's a district level softball player and an average swimmer? You know what I mean? You could calculate those Z-scores to determine that. Yeah. Mm-hmm. Okay. Okay. Yeah. Who was it? Yeah, in fact, yeah, do you want to look that up? Because I think that would be a really interesting thing to look at in terms of how we apply these standardized values. Good. These are all excellent questions, by the way. But this is what standardized values do. They allow us to measure things with a standard statistical unit rather than a variety of a bunch of different regular units. By the way, sports is not the only place where this applies. We could do it for who's the best student in the school, right? We could take your SAT scores, your GPA, your AP scores. We can put those on a distribution. We can calculate Z-scores, and we could add Z-scores up to find out who is the best student, right? We can do it for anything. I mean, anything where we need to compare some kind of statistic. Sports and academics just happen to be the easiest to talk about. Let's just compare values that are measured on different scales with different units or from different populations, right? It's really valuable tool to use for comparison. Okay. In fact, this is what my dad, who's a computer programmer, he ended up doing something like this to test computers. He'll write a program, and they'll test it on different machines to find out how long it takes for the program to compute, and it'll create a bell-shaped curve like this. And he can take a single computer and look at its data, calculate a Z-score for that computer, and be like, well, this one is this many standard deviations faster than other ones, right? Or you can take a single computer in a lot of different programs and run the same program on that one computer, and you can find out which one is most efficient on that particular computer, helping you find efficient programs. So again, we can use this to compare anything. Oh, okay. Do they give like the statistics that actually show like their methods on it? Do you want to post that link to the Google Classroom? And then maybe a lot of times they post their methods, but they do it in like really weird places. It's like a link at like the bottom of the page. So, all right. So an example of how we can use Z-scores to compare these things. We'll do one together here, and that'll probably be our day today. This was the 2006 Olympics, so the data's a little bit old. The men's combined skiing event in the Winter Olympics consists of two races, a downhill and a slalom. The two events are added together, and the skier with the lowest total time wins. So that's the way that they calculate the winner. They add them up, and whoever's just got the lowest score of the two added together wins. In the 2006 Winter Olympics, the mean slalom time was 94.2714, with a standard deviation of 5.2844. The mean downhill was 101.807 seconds, with a standard deviation of 1.8356 seconds. So these are the two sets of data. This is the whole distribution that calculates the mean and the standard deviation, and there it is. One of the United States skiers, Ted Ligety, won the gold medal with a combined time of 189.35. He skied the slalom in 87.93 seconds and the downhill in 101.42 seconds. So that was our gold medal winner. Which race did he do better compared with the competition? So if we want to compare him to the rest of the distribution, what did he do better on? And did I leave myself? I did not leave myself space. Now that's something that I'm going to need to remember for the future. Leave myself space to do it on the presentation. Oh, you can't because it's below where the thing is working. So yeah. I'm going to try and do the work up in this little space up here, so it'll show up on the recording. But we'll see how that works. So what we're going to do, so it says compared with the competition right there, right? And compared with the competition means that we want to compare it with the rest of the distribution. So we want to look at the Z-scores. We want to see how he did in comparison to everybody else. So let's calculate two Z-scores, and I'm going to need somebody out there with a calculator to help us out. Our Z-score formula was y minus y bar over s. So we're going to calculate each of these two Z-scores together. Let's do the slalom first. The slalom was 94.2714, standard deviation of 5.284. Ted Ligety did it in 87.93 seconds. So calculating that Z-score. My data value is 87.93 seconds, minus my mean, which is 94.2714, and my standard deviation for the slalom was 5.2844. Somebody want to work some calculator magic on that and tell us what that Z-score is? Negative 1.20. Okay. So we should read that as 1.20 standard deviations below the mean. And we know it's below the mean because it is a negative number. Okay, so that's his slalom score. Let's do the downhill in red. Okay, downhill information. We need the data value first. He did the data value in the downhill in 101.42. The average downhill was 101.807. and the standard deviation was 1.8356. And again, I'll give somebody a chance to work some calculator magic. I'm going to underline the relevant slalom stuff in blue. That way, when somebody's going back to look at it later, they can be like, oh, that's the blue stuff. Any calculator wizards out there get this one yet? Negative 0.2599. All right, so that's negative 2.599, 0.2599 standard deviation below the mean. Looking at those two numbers, comparing those two numbers, which event did he do better at in comparison to the rest of the competition? The slalom or the downhill? Slalom. Because this is a case where being farther below the mean is a good thing, right? That is something that you'll have to look at when you're doing examples, is when is it good to be below the mean and when is it good to be above the mean. If you're taking a test and we're comparing your test score to everybody else in the class, do you want to be above the mean or below the mean? You want to be above the mean, right? So you want a higher positive z-score. The higher positive z-score you have, the better. So we use z-scores, and the z-scores here told us that he did better at the slalom than he did at the downhill, because he was more standard deviations below the mean on the slalom than he was on the downhill. Okay, so this is an example of taking a single skier and seeing how much better he did in terms of the two events. Okay, what we will do first thing tomorrow is look at two skiers and compare their two events and see if maybe, in terms of how they did in the rest of the competition, maybe somebody else did it. So that's what we'll talk about for today. Homework tonight. I want you to try to do some z-scores tonight. We're going to discard those. Let's go ahead and